Okay, so as I said, Xcimer is a fusion startup company, Xcimer Fusion and Energy Corporation, and we are seated in Denver. And as you probably know about the successful fusion demonstration at NIF, the biggest laser in the world. And so our mission is actually to provide the next biggest laser in the world, which will be at the 70 times less cost compared to NIF, which will lead to the commercial fusion. And to start, I would like to provide some motivation about fusion. Why is it so cool? And in principle, the easiest thing to think about it is to take the Einstein's equation. And if you think about any reaction, and if you measure the weight of your ingredients before the reaction and the products after reaction, then you immediately extract how much energy you got from the reaction just by multiplying the difference by c squared. And the message of this slide, it's very important because I really prefer to name our technology hydrogen fusion instead of nuclear, because people very often confuse nuclear with radioactive. And so it's a mistake here, because fusion doesn't produce any radioactive waste. And it is also supported by the legislation that White House put actually fusion as a technology among accelerators. It is not like fission, where the burden of security rules is just amazing, and it prevents it from to be like really successful. The physical reasons for fusion are very obvious. It's been demonstrated that sun, or based on fusion, is the best source of energy. It's the most optimal reaction, and it's I have these two pictures just to demonstrate a little what it means. Fusion, that's the efficiency of the reaction is that in the red capsule, you actually store the energy of electricity for a year consumption of a small village. It's like 10 houses in Colorado. And if you say take the pile on the right of coal, it will be enough for one home, one house. And so it's very obvious it's not attainable to go with coal. And fun fact, coal actually, because it's so massive amount of combustion you have to do, that it contains some small fraction of radioactive materials, and in the end, it actually provides the same amount of radioactive waste from fission, which it's a little funny. And so my message or ask for you is actually please get the social license for fusion, because it will change the history. Now about Xcimer fusion, when we say fusion, we actually mean commercial fusion. And the difference is it is not just experimentally demonstrate we can generate 5 megajoules of energy right now. We would like to, and then do something. We'd actually like to go after a gain above 200, comparing the wall-to-wall energy in, energy out. And what it means actually for a customer, because once fusion is enabled, instead of paying $150 per megawatt hour, we could be paying as low as $40 per megawatt hour. And this would have dramatic consequences for the whole humanity. And also the power that it can provide, it's above 1 gigawatt. And so it's very challenging to generate a similar power plant. And my talk will be pretty much about the enabling technology for this power plant. And so if you see in the schematic of the fusion power plant, the long lines are actually lasers. And so it's tens of meters long lasers, and laser is actually what will enable the compression and preparation of the fusion reaction. I would like to acknowledge the team. So this is computational physics-oriented team. We need to target things like nonlinear optics, plasma kinetics, red hydro. And we use, of course, applied math and HPC and data science. Okay, so the thing how we call our effort is it's interpreted through iris, because it's a it's relevant to lasers. And Iris is a digital twin of our actual device being built in Denver. And so we expect to have first experimental shots roughly in a year from now. And Iris tries to be modular and tries to be user-friendly for customers. And so we have Fourier optics for optical elements. We have coupled wave system, which is based on finite elements. And we can couple it also with Emacs, which is the engineering tool where people can actually design things correctly. And this talk is pretty much about the coupled wave system, the stimulated Brillouin scattering, and it is based on MFEM, of course. Or it's not, of course, it's just about the best choice. It's MFEM, and we also combine it with Python and MATLAB and some other libraries we developed. And of course, MFEM plays essential role because we are doing big simulations, kind of. Now, let's explain a little the model. The difficult physics is stimulated Brillouin scattering, which means that we are able to compress light, in short. And in terms of mathematics, it means we grab Maxwell equations. They are actually nonlinear. There's also other wave equation for the gas. And we need to carefully or precisely model optical aspects like diffraction, self-focusing speckles. And the core of the SBS three-wave nonlinear optics goes through the electrorestriction force. And it actually means, if you see on the bottom figure, is if you have optical fiber and you provide grading, which changes spatially, periodically, the refraction index. If you shoot some light into this optical fiber, it will actually reflect some light back on a little different, it's actually the same frequency. And if you have a gas and you shoot it from both two sides with lasers, with two lasers at the same frequency, so they are going to superpose, and you are going to the pattern on the bottom, top right, and it's a standing wave in the end. So the wavelengths of the lasers will tell you what's the wavelengths of the standing wave. This will actually create grading in the gas, and it starts to reflect the both laser pulses going in. What's funny is if you start changing the frequencies of the lasers and you are actually pushing harder on the left side, so higher frequency means more energy, the grading pattern starts to move slowly to the right. And the trick is, if you move it exactly, it's like moving standing wave. And so if you move this wave exactly at the speed of the acoustic wave, you are in resonance, and suddenly magic happens, and you start completely extracting the energy from the pulse going from left, and it is being transferred to the pulse going from right. And that's SBS stimulated scattering. A quick thing about Iris. So we handle it through Jupyter notebooks. So we have this CWS library, coupled wave systems, and you import it. As a designer, you define what are the boundary conditions, the inflows, and then you run it. You get the result, and you can, like, I generated this result in Jupyter Notebook. Now, the very important thing is the reality of simulation. This SBS happens on the spatial scale of hundreds of nanometers. So it's the wavelength of our lasers is 240 nanometers. It's ultraviolet, so you wouldn't see the laser. It's very short. And as you could see in the schematics of the power plant, our beamlines are maybe 100 meters long. So it means even in 1D, if you want to interpolate correctly the wavelengths, you need to apply 1 billion doves in 1D. And of course, we are doing 3D. And so this would be just a nonsense. And so we do something as called high frequency separation, or WKB. There's different names. But in the end, you just separate the high frequency feature from the slow pairing and amplitude envelope. And this leads to our base model. So this one shows two waves. We already eliminated the gas. It can be done. And you start coupling different laser beams together. I should probably explain what it looks like. Yes, sorry. So the smileys are just they are protecting our IP. I didn't want to redo the figures. The point is, on the movie you can see the effect of FPS, because the point is you can generate very cheap, very long in time, relatively low energy density pulse, but because it's very long, it actually transfers a lot of energy. And the process of SBS is capable of compress this energy in terms of handing it over to a very short in time right pulse. So this you should see it on the movie. So you see the long pulse from left propagates, then it's crossed by the small pulse, and it slowly takes almost all of its energy. It's a very simple concept, but very important to provide strong conditions for to actually achieve commercial fusion. The simulations are actually kind of predictive. I will explain why we think so. So there is a couple of things how we can measure the validate our model and its results. So for example, we know that conserves energy. It transfers correctly the amount of energy from pump to seat, and everything matches nicely. And we are able to get to 40% of transfer of energy, amplification or compression. And the comparison goes also for 2D. So now I'm building up the knowledge, which it's a smart thing to do, actually, going from 1D to 2D to 3D. And so in 1D, we got some results, and we are now adding more and more physics or the geometry of the actual experiment. And so as you can see, the X means that we have the beams are non-axial. They are actually crossing the domain. And you can see three different times. So in the beginning, it's just the beams, the pumps are making it all the way through the cell to the right. This is when the seed starts going in. When it makes to the halfway, you can already see it's a similar intensity as the pump. And you can see it's stealing the energy from the pump. And at the end, the small guy on the bottom actually took, as we said, like 40% of the energy. And we are already learning about some very important features. There's the spatial distribution of the expected pulse. And then the same thing in 3D. This simulation has roughly 100 million DOFs and runs the time steps probably like 1,000 time steps. So it's already quite a heavy task. And again, you can see three different time steps. So the bottom left shows the moment where all the pump beams made it through the cell, reached the entrance where the seed gets in. On the way of propagating roughly halfway, it's picking up a lot of energy, and it means that you are actually starting to see it. And at the end, what we see, and we are very happy to see that the 3D gives very similar spatial profile, very similar amount of energy being extracted from the pump. And yes, it means everything fits. And so this is summarizing the effort. So we do 1D, 2D, 3D physics validation. It is set up for the realistic Phoenix. Phoenix is going to is the name of the device we are building. Like it is not going to be yet the biggest laser in the world, but it's the proof of concept of SBS compression. And our higher order finite element implementation gives very nice results that correctly go to the same physics in 1D, 2D, and 3D as expected. And the 3D already requires submassive parallel simulations on roughly 1,000 ranks. And so I would say we are very happy about this because it's a very important part of the deliverable. And then other things, there is of course some more physics. So I don't know if you know what is diffraction, but diffraction means that if you propagate light, the plane wave tries to curve a little, and if you have some corners, so it actually generates like it propagates some photons towards the shade where you wouldn't expected it. And so here you can see it. There is a very thin beam going from the left, and when it propagates over roughly 40 meters, you can see that it diffracts up and down. It's complex quantity, actually. Sorry, I didn't say so. The unknown is a complex system, so you have to have real and imaginary part. And so the top is real solution, bottom is imaginary. The good thing is that we have analytic solution for this case. It's so-called Gaussian beam, and so we are seeing that we are getting a perfect match with p equals 3 elements. So we found it's actually a very good tool for us. We have very smooth features, and so p equals 3 is great. If we're cutting down the cell by half, we are getting 16 times better result. Well, so we tested, we validated against analytical solution, and now we are very interested what the diffraction will look like in the actual experiment. And what's extremely important, like no one has done this yet, to understand what's the role of diffraction in the SBS amplification. And so we did the comparison with some realistic input. It's this guy, like this high frequency guy. So it's the input to our cell is propagated using the finite elements, and we compare vacuum and SBS amplified pulse through the gas, and we are happy to say, okay, we are actually getting very similar diffraction pattern, which is something that it's I would say it's a great success for MFEM, demonstrate this kind of thing. And after the SBS amplification, there is another part that is actually extremely important because the beam, when it's propagated, it's fairly huge. You know, it's like 20 by 20 centimeters. And the target when we want to do fusion, it's very small. It's roughly half a centimeter or maybe like a centimeter. And so there needs to be the focus, of course, which is ideally not done through the optics, which is would be like a very long story. But the point is we need to be able to also do the propagation of the pulse on the focusing part. And there is like extremely unfortunate or undesirable feature. Once you start focusing, your idea about separating the high frequency feature is gone, and it starts polluting your input condition. And so this high frequency guy, it's just actually very soft. It's a lens that is focusing over 50 meters, and we need something like 5 or 10. And so you can imagine that it can be like a disaster when you want to do precise simulation. And so I did some experiments starting with 200 meters lens, which is it's okay. The input is actually it's high frequency, but it's fine, and it's manageable with finite elements. But then it's very expensive, and we developed something based on coordinate transformation. And maybe short note, in principle, we are inspired by the Fourier analysis or Fourier transformation, which means you divide your signal or function into plane waves and you combine them together, and then you can calculate one by one because they are orthogonal. But unfortunately, it's not a good idea if you want to focus because there are these high frequencies pop up. But what you can do, you can probably introduce some better bases than Fourier and not a plane wave. And so we actually demonstrated something, it's called exact phase, but it's because focusing is similar to a spherical wave. And suddenly, if you redefine your system, you do this transformation of coordinates, and you are out of the weeds, and it's amazing. And so if now we go from 200 to 50 meters, And so you see that the plane wave just completely fails. And actually, if you want to satisfy the accuracy, you would require thousands of doves for the extra dimension in 2D. And if we go to even closer, which is the 5 meters, which is sort of our goal, so we can see that the plane wave is just completely garbage. There is no way we can get the solution correct. And you would require 10,000 points to, of course, this blue thing, there is high frequency feature, you won't see it because it is very high frequency. And so you would require 10,000 points into the, if you go to 3D, it's actually millions of points. And the funny thing is, if we do the transform problem, we call it here exact phase. So you can get a very precise result, and you need 1,000,000 times less doves compared to the plane wave, which is really cool. And the point is that it actually goes to the how we handle phase space, and we are trying to find the proper base to interpret our how we solve for distribution function, because wave, it's nothing else than like a moving particle in some direction with some energy. And so the transformation absolutely saves our butt. And so I would like to take this as a last slide, that the takeaway, at least for me, is using MFEM in combination with smart coordinates transforms rock. It's really cool, and we see it for our it's actually doesn't need to be spherical wave. It can be absolutely general wave. And in the end, this means it's a nonlinear system. So we go from linear Maxwell to a nonlinear system, but it saves us a lot of troubles. And the same thing we actually saw with BLAST, or in principle, the Lagrangian hydrodynamics. It also means that you are picking better coordinate system. It makes it nonlinear, but it's worth it. We know it works absolutely great. And last but not least is the case of general SN. So if you see the yellow red results on the bottom left corner, so the top left is very typical results where we see something called race effect. And if you go for it and apply some smart transformation, which you actually don't need to even define because it can be defined by itself, it's a nonlinear system. So then you slowly converge to the bottom right result, which is completely smooth, and it is actually the solution as it should be. And with this, that concludes my talk and prepares the space for the next for Jan. Oh, sorry, and I didn't say much about finite elements. So there is at least one bullet point describing how we do the discretization and some important specifics.